My name is Jessica Barron. I'm from the Riley Center for Science, Technology, and Values, and I'm very pleased to introduce our next speaker, Dr. Joe Fernando. Dr. Fernando is the Wayne and Diana Murdy Endowed Professor of Engineering and Geosciences at the University of Notre Dame. His primary affiliation is in the Department of Civil Engineering and Geological Sciences, and he also has a concurrent appointment in the Department of Aerospace and Mechanical Engineering. I don't have time to read the whole biography, but it's incredibly impressive if you go to his website. He served on a number of different committees and been in the press a number of different times, and he's published more than 200 papers spanning about 55 different archival international journals covering more subjects than I could possibly read to you right now. So please help me in welcoming Joe Fernando.
So thank you very much. Can you hear? Is it on now? Here. Let me see whether I can. Oh, it's on now. Okay. Thank you very much. Certainly, this is not my typical audience. Usually, I speak to fluid dynamicists, physicists, oceanographers, atmospheric scientists, engineers, but this is the most multidisciplinary I have ever been, probably. But anyway, when I was asked to talk about climate change, I'm not really a typical climate change scientist, but I have been keeping aware of what's happening. So then I look at the schedule. In the morning, we had all the science of climate change. And tomorrow you have the climate change, the sociological, the religious aspects. So I thought that I'm in that transition regime so that I can talk about both, which I don't know much about. But anyway, so I thought that I will start about the common good. This is one of the things I always thought about, and that's one of the things probably it made me to come to Notre Dame. But obviously, when you talk about common good, you have different definitions and interpretations. But I would like to dwell on one of the more intellectual forefathers of the Catholic Church, St. Augustine of Hill. He basically, in the 5th century, he talked about the common good. That means the working towards the well-being of the whole society, which is exemplified by providing people adequate good food, sound housing, the environmental aspects, safe water and air, healthcare, education, human dignity, justice, as well as sound social fabric, which is compatible but not against the natural law. So who is providing this common good? Obviously, ourselves providing common good for the mankind. So that means our actions, ambitions, needs, thinking, understanding, and our altruism basically determine this common good. So some people might argue that the actions are the most important. So that means all these other attributes, the ambitions to altruism, basically determine our actions. So what determines all these other things? Obviously, how our mind, as well as our human values, mind and our conscious, how they interact with each other, and our human values are determined by that. And this is how where we have the spirituality and religion come in. So all these things are really tied together. So spirituality and religion are also relativistic because some people have different values and different spiritualities and interpretations. But being a Catholic institution, I would like to more espouse into the Catholic teachings. But I'm not a Catholic scholar. We have priests sitting in, so I don't want to preach to them. But one thing really strikes me is few papal encyclicals, recent. One is this Caritas in Veritate by our retired pontiff, Benedict XVI, which is charity in truth, which really encapsulates what we should be doing as a society. Basically, he says the charity is extraordinary force in which leads people to do courageous and generous engagement for peace and justice. So that's basically, he calls, in the heart of the Catholic social doctrine. And then he talks about the relationships. The relationships are very important here because he talks about the relationship between the people, and if you are believing, it's God, as well as the outside society. So we have these micro relationships as well as the macro relationships. Macro relationships we always do, talking to your friends, family, and all these things. But the macro relationships are the ones which are very difficult to espouse because that involve the whole society. Relationship between you, your neighbor, God, as well as the political, economic, and social systems. So this is the one, at least when I teach, I try to get the students involved into that. So this was preceded by two very important encyclicals, this Popularium Progressio by Paul VI, as well as the one by John Paul II. But one of the very striking aspects, as I mentioned, is that chapter 4 of this one is talking about the environment. So he talks about the energy problem, energy hegemony, he called, that few people are controlling the whole energy industry. He talks about the whole environment. He talks about one earth concept. That means we all share the earth. And he laments about self-centered folks. He talks about people who think that we don't owe anybody to the society, although they like to have everything from outside, but they don't think that they owe anything to society, but they owe to themselves. So these type of concepts are there. And one thing is really remarkable is about Earth with no boundaries, the environment with no boundaries. For example, if you take the same molecules, Jesus Christ or Mahatma Gandhi or Winston Churchill, which they breathe, these are the same molecules we are breathing today. It goes across the boundaries, across ages. So we basically share a common environment irrespective of cultures, time, regions, economies. So we have that responsibility to make sure that it remains such. So the Pope calls very nicely, before it's too late, we have to create a strong alliance between man and earth. And he says we have to make a strong commitment to reverse those trends. Basically, the trends which basically leads to the decay of the society. And his predecessor was much more stern. He will calling Earth will not continue to offer its harvest. That means limitation of the resources. We cannot say we love the land and then take the steps to destroy it. Very powerful statements. And it just so happened this was from a homily in Monterey, California, September 87. It was almost coincident with that famous report, Brundtland Commission on the Sustainability, that says our common future, which was calling for the same set of values from the people, people's responsibility to our planet. Well, all these things require action. What type of action? Well, we have to basically one earth concept. We share our resources. If you take more from one, the other will suffer. That has to be the type of thinking we should have. Second, we have to understand the interrelationship between people, resources, environment, and the sustainability of all of us. Then the multilateral approaches. The colonialism is gone, imperialism, hegemony, all is gone. Now everybody is on a common ground, at least trying to be on the common ground. So that means this approach should be applicable to nation, cultures, regions. We cannot go and say we had to go to the same carbon dioxide levels in 1990 when there were some countries which didn't have any carbon dioxide in the 1990s. You cannot have this kind of unilateral decisions. Then we will have knowledge creation. That is the one which we are here, the creation of knowledge about natural law. So we can understand the natural law and live accordingly. That we use the understanding to bring up new technologies, tools. And also we have to teach people how to respect for scientific endeavors. Because science is at the heart of understanding. Engineering is an upshot of science. We take the things and put into practice. So that has to be one of the things. For example, science helps us to get into deeper insights into the functions of the natural systems. And science leads to sophisticated technologies. For example, satellites came in 1970s, and you can see how much it has revolutionized. Now we can look at the whole Earth as one Earth. Those days we go here and there and look for a few things, but now the whole Earth in a holistic way, we can look at them now. And then we had to have the ability to reconcile the human affairs with natural laws, which is always debatable, as you know. And then we had to somehow communicate that the science has helped us immensely. It warned about the ozone layer, and it saved from that disaster. It warned about the desertification, acid rain. Now it's warning about global warming. So we have to take science seriously. But one thing we have to also mention, that science is not absolute, because always science keeps on evolving. When Newton came up with the laws of mechanics, it had to be changed after 200-300 years later. So everything is evolving. The best knowledge, so if we want to wait till we understand fully, very satisfied, the airplanes won't be flying today. There won't be ships, because people use the best knowledge to get things done. But at the same time, there's uncertainty. That's the reason airplanes crash, the ships sink, or people die, because we don't have that absolute technologies and absolute science have been mastered. So we basically do the best science we can get. How much science is developed, that's a debate. So this is from the National Academy. You can see they clearly enunciated that we have to enunciate and we have to give the uncertainty of science before we do any type of societal action. So people will understand that. But of course, we have botched the situation sometimes, as you know. A few years ago, we had the Climategate incident. And here, people basically, some of our esteemed colleagues, have been rather wishy-washy. It was actually, they were accused of selectively deciding which data to be included. And it's still going on sometimes. It's quite amazing. Last two AMS meetings ago, one of the meteorologists got up and was complaining that the climate scientist asked him to move one of his stations, which is not very good. So we have to. So this is our own fault. And then some data stations have been moved around, especially in urban areas. Because urban areas are much hotter. So where the data stations are, very, very important. Because as the urbanization takes place, the hot areas will get out, and some of these stations will be hotter. So how do we decide these things? The best science, we have to look for these things. And also they were accused of, it's a religion rather than a science. Basically, it's like fox guarding the chicken coop. Basically, you say that this is happening, and then you give money to them, and they keep on propagating this. So how do we avoid this kind of misaction, which has really hurt the scientific community? That has to be discussed, and some or other make sure that we do the best science. People who don't know climate science should not be talking about climate science. In this case, in fact, these people know climate science, but they were trying to persuade public that this is a problem, but when you get caught, certainly the whole thing will die. So this is really a shame that so much people are doing so much research, but then suddenly one or two bad apples can create whole situation worse. So that's one of the issues. And we have a lot of political battles because climate change involves taking care of the nature. So you have to reduce, as Professor Ramanathan said in the morning, the carbon emissions. So the diesel trucks, we have to go into new technologies. We have this lot of effort and money will be involved. So there will be certainly financial incentives and financial woes will come in. That comes to political battles. So then the scientists get involved somehow. I think it's our duty to get involved. And then people get political assaults from various folks, and which was a discussion before. And that has to be some or other avoided. And if we do it correctly, I think we should be able to do it. But the panel was much better place to talk about these things. Well, now I got a little bit of science from this discussion. Where should we take the action? So as an engineer, I always look for solutions, although not always successful. But this action has to be taken global scales because it's a global problem. The second thing is that we have to see who is getting affected. So that's where the population centers come in. Population centers, of course, you know it's called urban areas, and the core of the population centers are called the cities. The cities have been developing quite rapidly. Past 2 centuries previously, a lot of people lived in rural areas, but the urban population has been growing rapidly. So since 2008 or so, we have more people in the urban centers than in the rural areas. So that's basically where the people live. So that has to pay some attention has to pay for those areas. And while the population is increasing in urban areas, a lot of megacities have come up. So these are the cities more than 10 million people. In the 1960s, we had only 2 megacities, the New York City and Tokyo. But you can see now we have more than 20 megacities, and many more are coming. So these are the cities which are at major risk because it has the highest concentration of people, and it has extreme dynamics because things are moving and moving, and it's prone to supply crisis, social disorganization, political conflicts, as well as the catastrophes due to natural disasters. So that basically has to be keeping in mind, and there are a lot of megacities are developing. Phoenix, Arizona, from where my erudite 2 colleagues from, is one of the places. It has really rapidly grown, and now the population for the past 2 decades, it has almost doubled up. And if you look from the space, so this is one of the former Center for Environmental Studies slide, you can see that these are the Aster satellite images, and you can see the city of Phoenix is right here. So this is the airport. So this is about 10:30 at night. You can see the city is much, much more warmer than its rural surroundings. So the color represents the temperature. So this type of heating of these cities are typical. So if you look at this Phoenix, it is in a big, thick layer of aerosols, and these aerosols are both good. Some aerosols, for example, sulfate aerosols coming from combustion, from biocombustion, and carbonaceous aerosols coming from trucks and other sources, which increase the climate change. So this is a microcosm of the whole world, you can see, and the whole city is covered by a carbon dioxide dome, what they call. So you can see, in these kind of cities developing, of course, the urban heat island is developing. That is, the cities are made out of mostly engineered material. They have very high heat capacity. So during the daytime, they absorb heat, and then toward the late night, they retain the heat. So at night, there's a big temperature difference between the urban and rural areas. So that's part of urbanization. And when you develop urban areas, also that you develop the land use change. So when you have this type of land use, the asphalt, the concrete, then what happens is the moisture also decreases. When moisture decreases, what happens? You have particles coming up. They call the fugitive dust. And that affects the respiratory illnesses. And the moisture and the heat island, they get together and change the rainfall patterns. And that is how things have been happening in Phoenix, Arizona. Of course, not all for the worse, but all the other cities do the same thing. So these are the carbon dioxide emissions from different cities. Chinese cities are the smallest, but US cities are the largest, but mostly contributed by the passenger transport, not the public transport. But when you look at the whole city, whole country, you can see that China and the United States are the most contributors for the global carbon dioxide, followed by Russia, India, and other countries. So, in conclusion, we have the cities, they are the epicenters of climate change. So we have to talk about cities when you talk about climate change. I come back to that a little later. And the second one is that when you talk about climate change, much less attention has been paid to cities. Why? Because people in cities think that this is a big issue. It has to be fought at a very high level, the government, international level, and lowly mayors and city council people cannot fight with this thing. But it really affects them. Then the issues are scientifically very complex. dealing with the global climate is much easier than dealing with the local climate. The modeling is a nightmare. Unless you are insane, you don't go to do these things. But anyway, somebody has to do it. Now, looking at the climate to local scale. So the global climate change is happening. This is happening because all these cities send carbon dioxide. They keep on going all around, as Professor Ramanathan showed you today morning. And that basically increased the temperature. So what happens is that increased temperature now transpire into the cities. So the global change transpire things in the city, and what is happening in the cities go into the global scales. And that keeps on doing it, and we go from bad to worse. Now, one thing from the IPCC is very clear. When things coming from the global scale to local scale, they have a tendency to amplify. So the cities usually, have higher global change impacts than the global scale, rural areas. Now, how do we determine this? Well, if you want to model the whole globe, what you do is you take the globe, chop into little pieces, boxes like this. Then you solve equations of motion, the energy coming in, you have to consider chemistry. But each of these boxes of these models is about 100 kilometers. So below 100 kilometers, the global climate models don't see. So how do then we include a city influence in the global model? So this is a very, very difficult task. So basically what I'm saying is, for a global model, area where the city is a black box. So how do you say this black box is affecting the whole climate? That is done by some assumptions. So the assumptions are called the parameterizations. So parameterizations, this last time I'm putting an equation, we have several set of differential equations. These differential equations determine the black box. The whole city is a differential equation. And we have AX, AY, KZ. These are the coefficients that determine how the carbon dioxide move, how the pollutants move, aerosols move. All these are determined by, among other things, by these three coefficients in different directions. Then that basically sends a signal to the whole world, and that is coming back to you. Well, the question is, so how do we find out these things? So that means we have to look at the urban areas very carefully. So that means we have to consider buildings. We have to consider green spaces. We have to consider all sorts of different activities. So we have to consider, in short, an urban system. The urban system has transportation, building, water systems, and all these things. They work with each other, and these things have to represent the whole city using few coefficients. So this is what people are a little bit scared to believe in these models, because we are representing the whole cubes using this. But this is the best science, so why not? We basically have been always relying on best science, right? So then the model predicts what you have, what you want. Temperature in the future, rainfall, the extreme events, and all sorts of things. Now, one of the very simple things I have been working with is called the DTR. So it's called the diurnal temperature range. That means at night, what is your temperature? During the daytime, you have a high temperature. At night, you have a low temperature. The difference between the two is called the DTR, diurnal temperature range. This is a very good climate signal to look at if you don't want to look at these huge extreme events. So what happens is, when the climate change is happening, what happens is this DTR keeps on decreasing. So that means at night, temperature increasing faster than the daytime temperature increase due to climate change. that means the difference keeps on becoming small and smaller. The night becoming hot and hotter. So this is one of the signals. Well, if you want to look at this carefully, here is a cartoon. So assume that you are in a rural area. Let's say climate change is happening. What will happen when you have, what's happening is that you have high clouds, because high temperature causes high moisture, you have a lot of cloud. So when you have the cloud cover, the radiation coming in get reflected back. So that means whatever coming into your rural area is reduced. So it's a greening effect. But on the same token, the ground gets heated, the radiation going out get reflected back. So the two opposing effects you have here. And the upshot of this is that the radiation, because of this radiation balance, the daytime temperature is increasing slowly because of these two opposing effects. Now what we are going to do is that we are going to put a city into that. Well, then we have other things coming up. So you can see how complicated things are. Now what happens is that you change the land use. You have concrete, asphalt, roofs. So the radiation coming in now get reflected more. They call a high albedo, things reflecting back. So that means it's a greening effect. Okay? But things coming up and the radiation get trapped inside this building. So it's heating the whole area. So remember that in a model, all these things have to be taken into account. So this is not a simple issue. And you have roads, you have vehicles going. It's heating. Then you have irrigation, cooling. You have the black roads, the asphalt roads. It's a heating effect. Then what happens is these areas are kind of rough because you have all these buildings. When the flow goes through, you have a lot of turbulence. This turbulence go and basically take air, hot air from above and take it down. So what we call, the cast and entrainment of hot air. So you can see now having a city has made all these differences to a local climate. That basically caused the daytime temperature in a city increase as fast as outside or a little bit faster than outside. So all these different effects. Now go to the night. Well, at night, if you don't have anything, the ground gets cool, the temperature is cooler, and you have a nice cool night. But the problem is with the clouds, when you have climate change, these clouds basically reflect some of the radiation back to us. That means you have warmer now than colder. This warmer air now causes less stable air here that basically take fluid from top, called entrainment again. So now you can see at nighttime, there's nothing coming in, whatever going out gets trapped, and that basically increased the nighttime temperature faster because of this climate change effect, which is coming from the clouds, increased cloud cover. So this is the reason DTR is decreasing. Now let's put the city. With the city, you have other things. Now the city is trap radiation, and the buildings keep heat because of the high heat capacity. And then these plumes are rising, coming from the sides, and take this hot air from the top levels and put it down. And then the upshot of it is that indeed, near the ground, in cities, not as cold, it is warmer. So that basically caused this diurnal temperature range decreasing faster. So compare the climate change, reduce this signal, DTR, but if you have urbanization, it decreases faster. Now, we can look at some data. My colleagues were looking at this. You can see two from Chicago and Phoenix. That's where actually we work, different funding sources. And this is the O'Hara Airport. And this is the DeKalb, which is a rural site. And in Phoenix, you have a lot of sites, good sites. This is the Phoenix downtown, and these are the outside areas. Now, look at this O'Hare Airport. Don't worry about all these details here. You can see DeKalb area. The DTR is decreasing. So really a climate change signal coming into that area. Now, O'Hare Airport is less because of urbanization. It's also decreasing, but it's not decreasing much faster because the urbanization already happened. So now the urbanization is there, it's decreased, and it's there. But in Phoenix, rapidly growing, you can see this is the outside. It's decreasing because of the climate change. Now, in the Phoenix downtown, you can see it start decreasing much, much faster because of the urbanization. So people living in cities get this uncomfortableness. They call the human comfort index is much less. Now, urban heat island, that's the temperature difference between your city and outside. You can see it's rapidly rising in city of Phoenix. Chicago, much smaller. It was about 4 degrees in 70s, and it hasn't increased much because urbanization happened and done. Nothing else coming in. So dynamic cities, you get all the dynamics of climate change as well as the urbanization. Separating these signals, not very easy. You have to go one by one. And this is, for example, this is an infrared camera one of my colleagues got. And you can see this is city of Chicago, and this is city of Phoenix. And the color represents the temperature. You can see the city of Phoenix at night. It is glowing, really glowing, and the cooling of the outside areas are happening much nicer. So you have a big difference between the cool outside areas and the city. And that basically is supposed to rise with the climate change signal. Now, Phoenix heat island studies have been done quite a bit by the ASU group. And they show that every 1,000 homes, 2.5 degree temperature increase if you have 1,000 homes in a kilometer or so. They have shown that every 1 degree Fahrenheit, there are 290 gallons per month for a single household. So you can see 1,000 houses, how many per month you will get extra water usage. And every Fahrenheit, the temperature rises, the energy use rises by about 1.5 to 2 degrees. So these are all signals of the urbanization that basically feed back into your climate system. And health, thermal stress, exhaustion, heat strokes, all those things, hospitalizations, all keep on increasing. And to this conference, the social justice issues. Most of the people live, poor people live within the city blocks, and they get the brunt of this climate change. Most of the more well-to-do folks live outside in outskirts, but the people who are in the city will get the brunt of this. Now, to look at these issues, we continue with 2 projects. One is here at Notre Dame. We have got some funding from the city of Chicago, and also is partly funded by the Environmental Change Initiative, to look at the heat island in Chicago. The question is, Chicago is quite proactive, at least used to be, that climate change signal will be very, very poignant there. The questions are, can we change these effects on the climate change effects on the Chicago area by having green roofs, or some type of very specialized pavements? Can you increase the pedestrian comfort based on certain changes to the urban fabric? And can we develop a meteorological app so people can take their iPhone and look at what is happening on every street, on every hour? So that was the whole gamut of the project. Well, you can see to do this, it's prediction. We have all the history. I know my history colleagues don't like the future, but if you want to predict 2050, we have to make the prediction. So the question is, are these predictions right? And this is the very, very heart of this climate change scientific debate. how good are our models? There's no way of predicting. You cannot just extrapolate, as Nancy Grimm pointed out. You cannot just extrapolate. You really need dynamics-based models. So what we started doing was we take the climate model. Climate models go up to 2100. So these climate models are not easy to run. They are run by people who have climate models. There are 23 of them, now it became 29 around the world. Here we have the National Center for Atmospheric Research, Princeton Geophysical Labs, few of them. So we take the output from the climate models coming out of the National Center for Atmospheric Research. So we have the climate every 10 years. So our goal, we were told to look at 2050, what is happening. So I'm not worried about making predictions because I'll be gone, but we try to do the best science. That, as I mentioned, these models predict 100-kilometer grids. So the city of Chicago is here somewhere, sorry, city of Chicago is here and within one grid point. So this whole area, we get one value for the climate. So that's all you get from the climate model. What is the average temperature? What will be the average velocities? Average stuff. 30 average. Now we have to take this and decipher, so what is happening on a 200-meter grid, which we can see and make some decisions. Then what you do is you take that and you put a new model inside called the mesoscale model. So the climate model now feeding into the mesoscale model. This is called a nesting procedure. Now the mesoscale modeling, usually these models are developed, you cannot go below about 200 meters. That's the maximum you can push because the science parameterizations are not good. It is understood and we are not going to try. So then you take that 200-meter grid and then put another model. It's a fluid dynamics model. Now go and try to compute every 2 meters. So downtown Chicago, you can go and look at every 2 meters what the temperature, and you can measure that current state. If the current state works okay, then we can go to 2050 and say, oh, we have some confidence here. So this is the modeling methodology. As I mentioned, I'm an engineer. These are the things I look for. So if you want to be a little bit more technical, what you do is you take this 100-kilometer grid, then you get few grids so that you have much better statistics. And then first you run a 25-kilometer grid. Then you get to a 5-kilometer, 1 kilometer, and then come to 200 meters and stop. And then we go and 200. So we have all these 200-meter grids, and then we go to places we like to study. So your sponsor or your champion has to go where it is, and we have selected 2 places. One actually downtown Chicago, one actually because of Jessica Hellman. She has a measurement program here in the Indiana Dunes. Then we go and stop that 200 meter. Now that 200 meter, we will go into a very, very fine scale model. And look here, very small areas. I would like to see every box here, but our computational resources are not enough. Here in the university, or the access we have is not enough. So we go a few places and look at them. Now, the area we selected was Lincoln Park area in the Chicago, because that's where the DePaul University, they have some measurement stations, and where the underground has some measurements taken. So we can go and check these things. Rather than talk, we have to make sure that this is working okay. And so these are the 2 measurement stations. Now, one of our students, Patrick Conry, he ran this model on a 2-meter resolution. And you can see how, this is for the March 13, 2012. You can see how all these city blocks getting heated up. And similarly, you can get the velocity fields for these things. So we can see for today, for past, and hopefully we get the future and hope that is right. With this, all these type of things we have to do, you can see you have to take with a grain of salt all these things. Then we compare. So this is the data comes from. We compare this 200-meter resolution ones with different places. You can see the red here is the model, and the blue basically is the measurement. So this is not bad at all, given the complexity of these models. And wind speeds, so this is the temperature. Wind speeds, we are not doing very well. So much to be improved here. And here, the wind speeds doing much better in the second station. So you can see this is the state now, all these things. Then also we have another project from National Science Foundation. It's called the Collaborative Mathematical Geosciences Project, where we look at that 200-meter resolution grids. Can you improve a little bit more? So what we do is now the current models, they don't have these urban areas very well resolved. That's the reason we are going into this very, very fine-scale 2-meter grid. Now we are including high buildings, low buildings, commercial buildings, rivers, freeways. Everything is included in the models now. And when you do that, things become very complicated. That's why we need to run this for 1 hour. We need 16 hours of computer time on a parallel machine. So you can see it's becoming more and more difficult. And that we have to include all those radiation coming and trapping inside these urban canyons. We have to include trees, the turbulence, all these things we were talking about. Well, once you do that, the result is not too bad, because once you put these new urbanization schemes, you get much more realistic things. So we applied this for Phoenix. You can see the heat island is very well taken up by this. Without that urbanization, good urbanization, heat island is not there in the modeling. So this is without urbanization, this is with urbanization. So what we really do is that to take this output, then you can do various things. We can look at the air quality. So these are some measurements I would avoid. And we can look at the air quality. So we can connect this to an air quality model and see how the urbanization, climate change affects the air quality of the area. So you can see here, this is without urbanization. With urbanization, you can see that this is ozone concentration in that area. You can see during the daytime, so this is the 8-hour average ozone, which is the EPA standard. You can see much higher ozone production in the East Valley here during the daytime, because you need the sunlight to produce ozone. So it's basically a lot of ozone compared to non-urbanized area. So things are changing because our temperatures are changing. And then you can do other exercises. Here what we did was we took the whole Phoenix and put a concrete slab. You can do it on the model. So suddenly the heat island increased by 4 degrees. And what happens? That earlier, if you remember, the pollution came here. Now the pollution patch moved to the West Valley instead of East Valley. So there's a regime shift. So all these things are possible, and the hope is that this type of models will give us some kind of idea what will happen in the future. Now, making this prediction and communicating to policymakers is not something which they like to see. Sometimes, especially if you say that in 50 years that your West Valley will have a huge ozone blob on top of it, that's where most of the people live, people don't like to hear. And also, then they can come and say, look, your models are so simple so far that this is not the best we can expect. So there is this two tug of war. You try to do best science, and then you have this issue of public policy and economics. The biggest issue to climate change, I think, is this uncertainty. You can see these models are not simple. They are highly parameterized. People keep on improving. But when we go and talk about we know everything, that will be a problem. For example, I can do a very quick example. I think I have 1 or 2 more minutes. Jessica, is that 2 more minutes? I was in the committee called the Louisiana Area Science and Technology Board after Katrina. Then they had to build up this big storm surge barrier. The US government now requires to pay consideration to climate change in any kind of engineering design. which is a very good thing, as you might agree. So when you build up this barrier, the width is 30 meters, 30 feet, height is 27 feet. So when you put the climate change, the only thing was included was the sea level rise. When you include sea level rise, the storm surge became 5 feet more. So that means from 27 feet to 32 feet, you have to increase the barrier. 500 million extra costs. So then a delegation was sent, look, you know, it's taxpayers' money. A delegation was sent to the modelers and asked, do you really believe that this is going to happen? Well, if it is 500 million, we are not very sure because of the uncertainty of the model. I mean, do you want to make that kind of investment? Because, I mean, how do you determine the balance between your science, because of the uncertainty, and your economics? But I think Army Corps of Engineers did a very good job. They had what you call adaptive scheme that for the next 10 years they designed for the climate change with the provisions that if the climate change continues in the present phase, they can increase the barrier. But certainly they did this extra 5 feet, so it's 32 meters, extra 500 million. But all the new projects now, what they call the adaptive management. So we basically do for 10 years and look how the climate change is happening. Based on that, you basically make decisions. So you can see for engineers, practitioners, climate change is an issue between the economics, the science, the uncertainty. So I hope that when the scientists talking about that, you have to consider all these different issues. Thank you very much again. So I don't know if there are any questions. Yes, please.
I'm Asad Stefan from Madonna University, Michigan. I'm very impressed with your presentation and with scientific investigation of the models. I think this is a good way of looking at the local climate, which is more convincing than looking at the global climate, because it is much more complicated when you are looking at the boundary conditions of the global climate. Different climatologists, they have different boundary conditions that will give them different results. And that is the problem with the climatic models. They do not agree most of the time. Mm-hmm. I want to ask you about...
I would change that this is the best we can do. So it's the best science. Still, uncertainty is very high. Am I right?
I think you are absolutely right. That is the real problem. I think the skeptics are always looking at the agreement of the models. And since there is no agreement, they always go ahead and say, well, there is no climate change. They don't believe in it. Mm-hmm. But it is existing. We are living through it. Mm-hmm. I want to ask you about your research. Did you take into consideration the upper air data like temperature, humidity, and winds, and also the atmospheric stability when you looked at the temperature changes at the surface? This is the first question. I wonder if you can answer me as I go along. I have 2 or 3 more questions.
Yes, the upper air actually data coming from the World Meteorological Network is included, actually it's called the data ingestion, into the mesoscale model. So upper air data is already included.
My second question, you looked at the diurnal temperature change.
Yeah. Okay, sure.
You looked at the diurnal temperature change. Do you have an estimate of how this impacts the temperature at Chicago and Phoenix? By how many degrees rise do you anticipate as a result of these changes in the diurnal temperature?
Well, the climate change part, as you saw, is we believe that the signal here coming from, the slow change here. So it's about 0.09 degrees for about 40 years. So that basically is the climate change signal. The rest coming from the urban signal, from the day.
And the last question I have is to deal with the actual energy budget, the local energy budget. Did you construct a heat balance of the local climate?
Yes, it is included. As you can see in the model, the whole heat balance up to a few feet is included. So basically, the radiation coming from the sun, they keep on bouncing, and also we will have the sensible heat flux coming from here, the latent heat flux coming from here, from the trees, the heat storage is into account, and every aspect of thermodynamics, at least parameterized.
Do you have numbers for that?
Oh, I can give you not right now. Yes, because the model spit out these numbers, yes.
I think we need to thank Professor Fernando for his talk very much.